Hey, you guys, you've got an error on your first slide.
Do we?
Yes.
The course number?
Yeah.
Oh, I guessed on that one. All right, well,
No change it now.
you'll have to
We've
excuse
already
us.
teach that.
Why don't you get started, John?
Are you ready, Carlos?
Yeah.
All right, good evening. We're the Lunar Skylight Rigging team. And we'll be talking about what we have done this semester with regards to aiding the Lunar Express. The team's Josh, Carlos, Christian, and me, John, with help from Steve. Thank you very much. So Lunar Skylights, extremely intriguing features that were discovered from LROs on the surface of the moon. What are they exactly? Unlike craters, which basically impact from other rock, one of the forms of them, they're holes in the moon. They're caused by volcanic or lava flow, which has hopefully tubes running out throughout the moon underneath the surface. And it's interesting because no one has ever actually been inside it, no man, robot, or anything. So it's good for a discovery for us to actually see what's going on there. The problems that is posed by this is how exactly are we going to get the information we desire from these skylights? How are we going to go into it is the number one big problem. So, sorry, keep that going. All right. So, what our job was to do was to find a way to be able to rig a line or tether from one side of the skylight to the other and be able to lower into the skylight. Now, initially when we started, it was a big team of us and the TyraBot guys, and then we split up because of how complex the actual task was. Beforehand we came and discussed the most efficient way to do this, or the best plan. So the idea that we had was using a Tyrolean traverse between the two sides, as you can see through this image. That on one side of this hole, there is a climber, someone who has held down some line, and on the other side is tied around a rock. This way you can have, imagine that's the TyraBot is climber A. Thus the TyraBot will be able to go across it like that. TyraBot obviously having sensing software on it, as they explained earlier. The advantage to this is that we can control it, and there's a lot of protection from dust and other like rocks and such. Now, once again, as I said, we split it up, and our job was to find a way to get a line or tether across and to anchor it. So we had to brainstorm and think of all the different designs that could potentially work. And so started off thinking, okay, what kind of mechanical system can we make? All right, well, we could probably make some sort of trebuchet or crossbow type thing that could probably work, and it would be good because it would be consistent, and you could calibrate. You could do it multiple times, many iterations if you fail the first time. The problem though with that is moving parts, especially with the dust that would come up from there. All the mechanics in there easily get stuck and mess something up. So another idea that we looked at was a pneumatic cannon system. This one had a lot less moving parts, less likely to get caught up on the friction, the dust. However, the temperature change and storing the gas itself posed a large issue, which we found not preferable to the mechanical projectile. But we still wanted to keep thinking, went to the next idea, which would be a model rocket system. Low cost, we could do a lot of tests, and keep having iterations of tests with different ideas. Problem is that not very accurate, we couldn't carry as much as we would like to. So we looked at all these things, like I said, trebuchet, like crossbow type, a ball launcher, pneumatic cannon, And after picking all of these apart, we decided to stick with the model rocket and go on there. So, Christian, want to pick up the next slide?
Yeah. All right. So, for our starting point with this project, and I lost my voice the other day, so bear with me. Basically, our starting point was we needed to basically design and build something that can support one of these systems. Like it turned out to be Rocket, so like we designed a launch pad that was capable of pan and tilt. It could be customized for a later point if we decide that rockets were not the optimal method of launching. We could equip it with another launching system, so it could be easily interchanged. And it needed to be durable, so it could like carry out multiple tests and repeat it. I just repeat it. So yeah, basically, this is the launch pad. Actually, yeah. Oh, no, that's right. This is the launch pad. It can do a pan and tilt. There are motors hooked up here, and on the underside that you can't see. And basically, there are two guiding rods that basically work towards repeatability of experimenting. We can shoot off, we can bring multiple, there could be more guiding rods than two. We can shoot off multiple rockets across the skylight. So we have multiple tries and attempts in that sense. This thing can pretty much turn a full 360 degrees. It has a full upper hemisphere range of motion, and there are encoders on each function, pan and tilt, so we can easily track position and where it's pointing. Another component to this is, however, the actual getting of the line across the skylight, and we have. What we did was we employed a steel cable that we attached to the bottom of each rocket when we launched it, and then that was hooked up to a spool of fishing line that we simply had a bearing inside and put a steel axle through that, and then had somebody hold that while the rocket launched. So basically, yeah, here's a picture of that, and yeah, basically what we had to do was. As the rocket launched, we had to control the damping, rather control the speed at which the tether was fed out of the spool, so tangling didn't occur, and so that the rocket didn't really, or so it just stayed in a straight line. Yeah. And now Carlos will talk about the electric.
So the electronics are fairly interesting. So we can do pan and tilt. There's two encoders on it. We can track the exact position of this thing. There's debounce in it, so we can track exactly where it's going. And basically, as you mentioned, we have 360 degree pan and 180 degree tilt, 135 or so. So basically, what we can do is, this is a video of it working, and we'll show you afterwards because we need to plug it in and stuff like that. So basically, here we can see it has full range of motion.
Here you can see the motor attached to the bottom, working, moving it inside, and then the one on top separately, causing the tilt. That's it. And yeah. All right, so do my show.
We need to do that too.
All right.
Okay, so we want to take all this outside and do a field test. The location of the field test was Robot City. We discovered this nice, about 50-meter gap between two sort of plateaus, which we said roughly approximates a medium-sized skylight. Here's just another perspective of it, and you can see in the top, here's a picture of the flight trajectory of the rocket crossing the road from satellite imagery. So over the course of the semester, we conducted 6 field tests. On the final field test, we did 12 launches. The best deployment distance of the tether was 51 meters, and on average, we achieved about 31 meters. And just for fun, if we didn't attach it to a tether, we were easily able to go across the Monongahela River.
Which actually happened.
Yeah. So here's a photo of one of the launches. Sorry, Google presentation, kind of annoying.
We kind of lose.
Yeah, I'll play that again. Most of the launches looked something like this. And then that one you couldn't really see the line, so we have another video where you can watch the unspooling. So you can briefly see the line. Okay. All right, so challenges we faced. So the biggest thing was with spooling, as we learned. The basic spool design worked very nicely. It was very low friction, not much inertia. The problem we ran into was that if it was completely undamped, if the motion of the spool was completely undamped, the line would tangle as the velocity of the endpoint changed around and the tension went negative or positive. And that just caused the rocket to crash into the ground. And then if we applied damping, you had to be careful because if you applied too much damping, it could create extra tension, especially early in the launch, breaking the line. And of course, too much tension also just limits the distance that you travel because you're creating this unnecessary resistive force.
Yeah, if you noticed earlier, we had a fishing reel as like part of our spooling, and issue with that was we couldn't do a successful launch with the fishing reel attached without it breaking. And
Yeah.
so it turned out that whenever we used, the spool that we showed in the video, it attached to the rod on that bearing, that it was actually able to stay connected as opposed to with the fishing reel.
Yeah, so what we found was that a constant damping, which you achieve with a fishing reel, didn't work out very well because the damping seemed too high early in the launch. And what we found worked better, though it was kind of unreliable, was just using someone's hand to apply resistance. And sort of, with repeated launches, we got better at this and had a higher success rate. But ultimately, this should be automated. And then also, there's just a necessary mass of the tether. And that mass contributes a small but significant downward force on your projectile. So ideally, you want the impulse in your rocket engine to be significantly larger than the mass of your line. And for our setup, it wasn't quite the case. So future testing would be best with a larger impulse. Anyway, so some more about future work. Our control scheme is very basic. We know we want to cross this canyon, and we have a simple model of the system, a point mass flying through the air, and we figure out some angle that we would want to launch at to get that distance. Ultimately, to get accurate with this, the model needs to get more complex and whatnot. And ultimately, we would like to explore anchoring further. So we did some initial things at the beginning of the semester. We found that dead weight anchoring might be one of the best methods to pursue. And we started doing some stuff with regular simulant, but that's mostly future work. Questions? Oh, so we have a demo